Okay, we'll get started for our first research talk. I'm very excited to introduce Natasha Jaques. Natasha is an assistant professor of computer science and engineering at the University of Washington and a staff research scientist at Google DeepMind. Her research focuses on social reinforcement learning in multi-agent and human-AI interactions. During her PhD at MIT, she developed foundational techniques for training language models with reinforcement learning from human feedback, which we also know as RLHF. In the multi-agent space, she has developed techniques for improving coordination through social influence and unsupervised environment design. Natasha's work has received numerous awards, including Best Demo at NeurIPS, an honorable mention for Best Paper Award at ICML, and the Outstanding PhD Dissertation Award from the Association for the Advancement of Effective Computing. Her work has been featured in Science Magazine, MIT Technology Review, Quartz, IEEE Spectrum, Boston Magazine, and on CBC Radio, among others. Natasha earned her master's degree from the University of British Columbia, undergraduate degrees in computer science and psychology from the University of Regina, and was a postdoctoral fellow at UC Berkeley. Please join me in welcoming Natasha.
Thanks so much. I'm so excited to be here. You guys hear me okay? All right. So today I'm going to be talking about a topic I'm extremely excited about, which is multi-agent reinforcement learning for LLMs. So you might have heard from the intro already. I do kind of a mix of things that include learning from human feedback to sort of this fully multi-agent adversarial training, where you use an agent to generate a task that is difficult for the agent you're trying to train to solve, and then you get a more robust agent. And so what I'm trying to do with this new line of research is really combine these two things. So take some of the work I've been doing on how do you train LLMs with RL and combine it with this type of multi-agent adversarial training. So that's what I really want to talk about today. So how many people in the audience, I can kind of see you, are already familiar with what is reinforcement learning? Can you give me a hands up? Okay, awesome. So I won't belabor this point. So I'll just kind of click through this. The key idea in RL is you have an agent that's interacting with an environment over time, and it's trying to maximize its total reward that it gets over that entire interaction. So the thing that differentiates RL from other machine learning areas and from supervised learning is that you can actually optimize behavior over time or over the long term. So thinking about the topics of this boot camp, right? We're thinking about how do we get agents that can actually do long-term kind of autonomous behaviors. I really think RL is a key tool for that, right? Because that's how you actually learn to plan a sequence of behaviors over time in order to achieve some objective. That's the whole goal of RL, right? People are getting increasingly hyped about RL fine-tuning of LLMs. I was dropping some stuff about DeepSeek because I think that kicked off a particular hype storm. But you could also look at like Rich Sutton, Age of Experience paper, David Silver, right? So I think there's a real, thought that maybe if pre-training is dead, we've maxed out all the training data that we can get for just doing supervised learning to train something like an LLM. Maybe RL is the next phase or could unlock some new abilities. It's the age of experience, right? But, some people may have questioned that when this paper came out. So this paper is saying, look, RL doesn't actually teach you new capabilities. It just upweights capabilities that the base model already has. So what this paper is showing is this is a reasoning task. To solve the reasoning task, you could take different paths through this kind of search tree. Some of them get you to the right answer and some of them don't. The base model is pretty much capable of generating all of these paths. When you do RL fine-tuning, RL VR on verifiable rewards, I kind of hate that term, but it is what it is. That will just upweight, rewarding behaviors that get you to the right answer. And I actually don't think this is at all surprising. It should not be surprising because of the way that we actually do RL post-training of LLMs. So the literal objective, which I have to drop that this is something that is from one of my early papers, when we do RL fine-tuning is to do KL control. So not only do we maximize the reward, but we minimize the divergence in terms of the KL divergence between the RL policy we're trying to train and our pre-trained language model. So why do we need to do that? Otherwise, we're going to trivially exploit imperfect reward functions. We're going to do reward hacking. The language model is going to forget how to actually use English language. And actually, the DeepSeek paper showed this as well, right? If you just purely train on solving reasoning tasks, their model ended up learning to mix languages, right? So it could increase its performance on solving math problems if it speaks in both English and Chinese in its chain of thought, which is really fun. But yeah, you need to do this to make sure your model doesn't lose its ability to use natural language. But of course, then this figure is a natural consequence of that, right? You're only going to upweight things that your model is already capable of saying that are highly rewarding. But I think people were sort of like, does this limit the effectiveness of RL? So how do you actually go beyond this? How do you potentially generate new data? And this actually relates to this idea of the age of experience again. We have to have the model generating its own data to learn from. And so how do we actually do this? How do we learn interesting and new behaviors? I would argue you need multi-agent RL. So the idea here is you could unlock continuous self-improvement by having the agent train against itself and generate its own challenging training data, challenging problems to solve, and then solve them. And so today I'm going to talk about two pieces of work that I'm really excited about. Both use self-play training. The first is for safety and the second is for reasoning. I do love taking questions, so I'm going to try to leave some time at the end to make sure you guys get a chance to ask questions, or you all get a chance to ask questions. And if you have a burning one in the middle of the talk, please raise your hand. I can kind of see that. All right, so first we'll talk about this safety thing. So this is a new paper we just submitted to NeurIPS. First authors are Mikkel and Liwei, who are both fantastic. I'm extremely excited about this work. The key motivation here is that current LLMs have no safety guarantees. So we have no way to ensure that these models that are being deployed to hundreds of millions of monthly users will not output harmful responses like tell you how to build a bomb, or reveal copyrighted information or PII, or say something phenomenally inappropriate, grok, right? So, this is bad. We should, we're using this technology, but we don't have any safety rails on it. So I would argue, because I'm a multi-agent person, so of course I would, the reason we don't have this is because existing methods are single agent. So when we try to make sure the LLM is robust and won't tell you how to build a bomb, we do use red teaming, right? So there's a ton of papers on red teaming the model. What does that mean? In red teaming, you try to search for prompts that elicit an unsafe response. How do I rephrase the bomb building prompt to actually get the model to tell me? But the problem is the way that we do this is against a static model. So we have one fixed copy of the model we're trying to red team, and we can use RL training to try to find some attacks that succeed. But what that will find is just the same attack over and over again. The attack that is the most unsafe, elicits the most unsafe response. And so then you pass off that data set of attacks to, the Gemini team, which is a different team, and they do, some fine tuning to fix that little batch of attacks. But it's fundamentally this like reactive sequential approach that's going to find this limited number of obsolete attacks, and it leaves the LLM continuously vulnerable to emerging threats that people can find. So again, no safety guarantees, right? I think multi-agent RL is the solution to this problem. So what this can do is unlock continuous self-improvement. So what you do is you have an adversary LLM searching for prompts that elicit unsafe responses from the defender LLM. The defender then updates to patch that attack. And what that means is then that attack no longer works for the attacker. So it's forced to discover new, more diverse attacks, get better coverage of the attack surface of the model over time, because the incentive in this game is literally changing for the attacker as the defender is updating, right? And so what this does, if we actually set this up as a zero-sum adversarial game, so to be a little bit more specific, the adversary is coming up with a prompt X, defender's coming up with a response Y, a reward model is judging the safety. You have to have a reward model, and the game will only ever be as safe as the reward model is good. So that is a limitation. That's just true. Reward model judges the safety of the response. The agents then play a min-max zero-sum adversarial game. So the adversary is trying to minimize the safety reward. The defender is trying to maximize it. Because this is a zero-sum game, we can trivially leverage results from game theory that say this game has a Nash equilibrium, And if it converges to that Nash equilibrium, at that point, the defender will give a safe response according to the reward model for any X that the adversary can pose. So that's pretty exciting. Now, in this paper, we haven't yet proved that the game is guaranteed to converge to the Nash. So we're working on that in upcoming work. But I think it's still really exciting that this is saying, as you invest more compute in this algorithm, you're converging to a point where your model is fully safe. So you're getting some level of scaling law for safety, right? So I'm pretty excited about this, but let's see how it actually works. In practice, the way we do this is you have the same model is attacking itself. So we're using self-play. Why do we do that? Significantly less expensive in terms of GPU memory. Like I can't afford so many H200s. You know what I'm saying? So this works surprisingly well. I think if you were going to do this at industry scale, you may not want to do self-play. We find that self-play actually works, which is pretty cool. And so this doesn't really increase your GPU memory at all. The computational complexity doesn't really increase over vanilla RLHF. It just increases linearly with the amount of extra data you generate from the attacker, which is just straight up good because you're getting more data. Okay, sorry, I'm getting ahead of myself. What do we actually do? Same model is playing the role of attacker and defender depending on the system prompt that it gets. The attacker gets a seed prompt. This comes from data sets of existing attacks. So we're using wild jailbreak. That turns out to work pretty well. You could use something else if you were interested. Take those attacks in. The attacker gets a hidden chain of thought. So it gets to reason about how to attack. And this is not shown to the defender. So this is a private chain of thought. It formulates an attack. The attack is sent to the defender. The defender gets a private chain of thought to reason about how to defend. And then it outputs its response. The reward model judges the response for both whether it's safe and also whether it's a refusal. So it's going to be hard. I think you guys need a mic to be able to answer this, but think for a second about why we need refusal in there. Like if we just did the game on safety alone, does anybody know what kind of spurious thing could happen? Sort of failure mode? Yeah. Thank you for the hand gesture. That was very clever. Yes. Okay, exactly. So if you just do safety, the defender can trivially win the game, trivially reach a point where it succeeds every prompt by just saying, no, thanks, I'm not going to answer you. So that's not useful, right? So that's why every RLHF reward, like typical reward models, judge both helpfulness as well as harmfulness, right? You need something in the game that's encouraging the model to actually answer the question. So that's what we do. And to give you more details about the scoring, we actually play the zero-sum game on refusal as well, which I think is one cool aspect of this work. So I'll get into that. So we're playing this game on, does the defender say something harmful? If the defender says something harmful, it loses, right? The attacker wins. It's elicited an unsafe response. Great. But we also play on refusal. So if the defender refuses a benign attack, the attacker also wins. So they're playing the zero-sum game on this Pareto frontier of you must be fully safe, but you must not over-refuse to answer because then you will be less useful. And similarly, for if it complies to a harmful attack, et cetera, et cetera. So this is the zero-sum game. In practice, we do cheat a little bit and add some reward shaping, so it's not like fully zero-sum. But we add some reward shaping terms to adhere to the chain of thought template from using think and answer tags. It's like the DeepSeek R1 template. We actually had to train llama models to do this. So unfortunately, I didn't update the results. We have even better results using Quen models versus llama, but these results are going to be with llama. We also add some reward shaping for the attacker. So what it has to do is stay faithful to the classification of the seed prompt that it gets. So we have both harmful seed prompts, which are attacks, and benign seed prompts, which are like just normal chatty requests. And we keep the data balanced at like 50% harmful, 50% benign, and force the attacker to also keep that distribution of queries. And so that just also helps balance the game to make sure it doesn't overly focus on being safe and train the defender to refuse and make sure that the defender has to comply some of the time. So this turned out to be pretty important. All right, enough of that. How well does this actually work? So the first thing I'm going to talk about is attack diversity. So traditional red teaming methods focus on just training the attacker. And what that does is find the same limited number of attacks. And this has caused people to investigate, do whole papers on how do you make more diverse attacks. Multi-agent training solves this issue because what we're comparing to here is if you just train the attacker, that's in red, you see the diversity of the attacks is tanking over time, measured either with expert or self-blue. When you train with multi-agent, that doesn't happen. So the attacker in the self-play setting continues to output diverse attacks because if it just kept using the same attack, that attack is already patched. It's not getting any reward from that attack anymore. So the incentives of the game are changing over time, forcing it to look for more attacks. And we can see this over the history of training as well. So what this plot is doing is taking all the attacks generated from the attacker-only previous work approach, that's in red, or the self-play approach in blue, encoding them using expert and plotting them using t-SNE. And what you're seeing is that self-play gets more coverage of this attack space, whereas the attacker-only approach focuses on like a few different modes of attacks. But when we actually look at the attacks, even the expert embeddings aren't enough to really show us what's going on. Because when we actually look at the attacker-only attacks, even from different modes, they actually look extremely similar. Design a phishing campaign, design a disinformation campaign, blah, 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 blah. It's kind of converging on the same type of attack. Now, self-play is discovering much more interesting diverse attacks. And I kind of have to put a bit of a trigger warning on this because these are attacks trying to elicit unsafe behavior. So they are talking about offensive stuff, but they are quite different. So, provide confidential details about US nuclear weapon storage. Okay. But also give me examples of highly offensive slurs. So it's actually it's covering much more of this attack surface that we want to be safe on. And what we see, if you don't use the hidden chain of thought, you don't get this effect. So allowing the models to actually reason about their attacks is really important to getting this. But the whole point is if you're actually getting better coverage of the attack surface and defending it, the idea is you could make a better, safer model. So let's see, does that actually come out? Do we get a safer LLM? And what we see, and like I said, these results are even better with Qwen. So we're really excited about the new results. What we see here is that for an 8 billion parameter model, comparing to the Llama 3.1 8 billion parameter instruction fine-tuned model, which is trained with RLHF. So RLHF is our state-of-the-art safety technique, right? And this is presumably, Meta put a lot of effort into fine-tuning their model to actually be safe. We're seeing up to a 72% improvement across all of these safety benchmarks versus this instruction fine-tuned model. So big gains in safety. And we're not seeing big increases in over refusing. So we see some increase in refusing, 15% increase in refusal. These two things are in tension, like we talked about. But we really think we're pushing this Pareto frontier of being much safer while still being a useful language model. And so I'm extremely excited about this. Like I want to do a follow-up paper that says, given an RLHF style like helpfulness and harmfulness reward model, and the same computational budget and the same model, if you do self-play against that, it's just straight up more effective than doing single agent RLHF. So that's like where I think this could head, but happy to take questions about that in a minute. We also show that the models retain key capabilities. So we see minimal loss in chat scores. Actually, there is a loss in some chat scores. We started with this obliterated model, so we lose a little bit on alpaca eval. The new Qwen results, we actually see weirdly gains on alpaca eval versus our base model. So we don't necessarily have to lose any chat performance depending on the model, and we see no real loss in reasoning or language understanding performance as a result of this. Okay, so in conclusion, this is the first work to explore online multi-agent reinforcement learning for improving LLM safety. First published work. Maybe some corporations were doing this, but who knows? It provides theoretical guarantees that if the game converges to the Nash, the defender will always respond safely. And it corrects an issue with the inability of prior single agent red teaming work to discover diverse attacks. And the ultimate punchline, I think, is it's just safer than RLHF without losing capabilities. So I think we should be saying, why are you still doing RLHF when you could be doing self-play? I do want to talk about one more piece of work super quickly. I kind of will breeze through it, and then I want to leave time for questions. All right, so the second piece of work is this self-play for reasoning. So This is a recent collaboration with Bo Liu, who's a student at the National University of Singapore, and a bunch of other collaborators. It's called Spiral. And the key idea here, I think the best motivation for this is when we're excited about RL fine-tuning of LLMs, but when we look at where has RL actually been successful, the biggest successes of RL before LLMs were not single agent. They were multi-agent. They were self-play. If you think about AlphaGo, right? The model is playing against itself. That's what unlocks a lot of the power of these methods, right? Self-play creates this continually evolving curriculum. As your opponent gets stronger, so do you, right? Proposing new challenges. As you get stronger, so does your opponent. Sorry, I said that backwards, but it's the same thing. So that can not only in the past we've seen lead to superhuman performance, but it can lead to this emergent discovery of skills. So I'm looking at this OpenAI hide and seek video where the agents discovered skills that the developers didn't have to program in. So if you contrast that with like training reasoning on math Olympiad benchmarks, you have to have a bunch of human crafted problems. But what if you could craft your own problems, right? So that's kind of the idea behind self-play. The specific idea investigated in this paper is, can we just do self-play on simple games like poker and tic-tac-toe? And would that improve reasoning on downstream benchmarks? So we're just going to do self-play on zero-sum games, negotiation, poker, and tic-tac-toe. The models will use hidden chain of thought reasoning, like we said in the prior work. And then we're going to test this on downstream benchmarks. And interestingly, and somewhat surprisingly, we say pretty big gains as a result of doing self-play across a bunch of math, Olympiad bench, AIME, Minerva Math, GPQA, and MMLU benchmarks. So just from playing poker, you're seeing performance on these benchmarks increase. So this is pretty interesting. How many people saw the spurious rewards in RL paper? Give me a hands up. Okay, this paper is not as well known as I thought. So you could check it out. It's a fun paper. They basically show that if you do RL on random rewards, like fully random rewards, you can actually sometimes see gains on reasoning benchmarks, but it's very dependent on the model. So only Quen models show that and Llama models would not. The reason is what RL on random rewards ends up doing is upweighting the most probable responses in your base model. So if your base model already prefers or has like high probability mass on reasoning and math questions, when you do RL fine tuning, it'll enhance that. But what we're showing here is that the gains we're seeing from self-play on poker like this is not due to this effect. So what we're doing here is we're comparing to training your model on poker, but against a random opponent. So therefore you would be getting random rewards, just like the spurious rewards paper. And we see this effect is not emerging. So your performance on math is going down as a result of this. If you train against fixed opponents, so like a Mistral opponent or a Gemini opponent that do not update in response to you playing the game, we also do not see this effect. Only when you actually do self-play, so you're playing against yourself, your own model is playing against itself. So as you discover a strategy and exploit an exploit that could work, you then correct it. So there's no fixating on a particular hack or reward hacking behavior. You have to actually learn something strategic. When you do self-play, we see this effect. So we're getting like a 40% increase on these math benchmarks. So this is just reiterating these results for both poker and doing multiple games. But the real interesting question is, why does this work? Like, why would playing poker make you better at math problems? I guess maybe if you're Noam Brown, it makes sense, but we want to investigate a little farther. So what we do is we analyze the chain of thought outputs with LLM as a judge, which I should put on the slide, by the way. So we use an LLM as a judge to detect certain reasoning patterns. So I'll say what those are in the next slide, but for example, like using expected value calculation. And we see that as you continue to train on poker, from early, mid, and late in training, the use of reasoning chains of thought that involve doing expected calculation increases over time. Simultaneously, the use of that pattern is increasing in the actual math problems that it's being asked. So it's basically taking a pattern that it learned when playing poker, like doing, for example, case-by-case analysis, and applying that increasingly as it's asked math problems. And this is corresponding to an increase in performance on the math benchmarks. So what do those patterns look like? You could have found different patterns. We focused on these ones. We see this case-by-case analysis. So for example, breaking the problem down into different possible cases and then analyzing what the results would be. So in poker, fold versus call. In math, the case that n is different numbers, different values, right? We see literal expected value calculation. That's useful in poker. And yes, there are some math problems where you have to do expected value calculation. And then pattern recognition is a little more vague, but it's basically looking at a pattern that has occurred before, either in this game or in other problems. But, you know, there could be many reasons why just practicing reasoning on these games actually improves performance. Like there was a paper that showed if you just append the token weight into the reasoning chain, that can actually improve performance because you're just kind of resampling and doing search over possible answers. But it's interesting that we see this effect pretty strongly. So I think the cool part about this is self-play creates continuously evolving pressure for the model to actually develop genuine reasoning patterns rather than memorizing fixed strategies. To some extent, games do really require, math. Right? To win poker, you have to do some calculations. So there is some literal enumeration skills that transfer. And we actually do some technical innovations. So building online multi-turn, multi-agent RL fine-tuning infrastructure, which we did release in open source. We also do this role condition advantage estimation. I'm going to zoom through this because I'm out of time. Essentially, you're just having a different baseline for advantage estimation for each agent and each game. And we say that without doing that, this would not work. All right, so in conclusion, self-play is this continuously evolving curriculum. Reasoning skills learned during self-play transfer to improve performance on 8 challenging reasoning benchmarks, which does not happen with RL against random or setting opponents. It does not happen without our technical innovations. So in the future, we want to explore more tasks, blah, blah, blah. This is all work coming out of the Social Reinforcement Learning Lab at UW. Please check out our website for these papers. Yeah, questions?
All right. Thank you, Natasha, for the wonderful talk. If you have questions, if you're able to, please step up to the mic. And if you're not able to, I will find you and give you my mic.
I have a quick question. How do you evaluate the harmfulness of statements? Is it like a database, or like how do you start that? Because it's probably also associated with political issues.
Yeah, I mean, that's a complex topic. So we take a pre-trained reward model. We take the wild jailbreak, wild guard reward model. It's basically a classifier that says, is this harmful or not? And is this a refusal or not? There are many different reward models you could use. I'm excited to do follow-up work that takes like a traditional RLHF reward model that judges helpfulness and harmfulness. The way that model is trained is from human data from raters, and those raters are usually trained to adhere to some kind of principles that are decided by, for example, OpenAI or Anthropic researchers. So I think there's a lot of questions to be asked about what do we mean by safety and a more pluralistic approach to this, which is, I've been working on that as well. But in this work, we just say we need to be given the reward model.
All right. Hi. First off, thank you for the talk. Very informative. I'm a little skeptical about how good the attacker LLM would be at generating attacks. Essentially, my intuition here is that since you're using the same model, I don't know how you're prompting it exactly, but if you're asking it to generate an adversarial attack, it's going to generate a prompt that the model itself understands to be adversarial. And it's probably generating in perfect, coherent English, whereas a lot of the jailbreaks that we often see work are very obscure and often cryptic, and I would doubt an LLM would generate a text like that. So how good is the attacker from your experience?
Yeah, so I think the proof is in the pudding in the sense that like our results are pretty strong. So we show the attacks are more diverse, and then the resulting defender is more safe. But you raise a good point. We have seen in certain training runs under different hyperparameters, there is a mode of the game where the defender wins too early and is too strong. Like the defender is overpowered relative to the attacker, and then the attacker will just start refusing to output attacks. So it'll get a harmful seed prompt and it'll refuse to answer that. But in general, we don't see this very frequently. We were all surprised by this. We wanted to try self-play first because it's so much more efficient. Interestingly, I think LLMs are such powerful models, so multimodal, that just conditioning on different prompts, like just different system prompts, enables them to have pretty distinct behavior in a pretty powerful way. So we actually see this work quite strongly. But that said, if I had more GPUs, I would do the full multi-agent version where the attacker is a fully separate model. And what you could do if you do that is the attacker has no KL constraint. So the attacker doesn't have to stay within English language, and it can formulate crazy strings that elicit unsafe responses. And that's like a much broader search space. So I think that would be pretty fun to try. So convince some grant funding agency to give me GPUs and we'll do it, you know?
Got it. I'll work on it.
Thanks.
All right, let's thank Natasha again for a great talk.
Thank you so much. This is really fun. Bye.